Okay, yeah. Thanks for inviting me. I'm happy to be here telling you about our result on eliminating intermediate measurements using pseudorandom generators. This is a joint work with Ross. So I'll start by giving you a quick preview of our results, and then I'll go on to describe what our results mean. So here are the two results I'm going to be talking about. Our first result is that quantum algorithms with unitary operators and intermediate measurements can be simulated by algorithms with only unitary operators and without intermediate measurements in very small overhead in time and space. So in particular, if you have quantum algorithms of time t and space s, we can simulate them without measurements in time T.poly s and space S.log T. So in other words, we give a version of the principle of deferred measurements that is both space efficient and time efficient. So this is our first result. Our second result is that we study pseudorandom generators for space-bounded quantum computation. We prove that a variant of the Impagliaso-Nissan-Wigderson generator folds quantum algorithms of small space. So now I'll go on to describe the background about these results and what they actually mean. So let's start with what are quantum algorithms of space S and time t. So there are many ways to define quantum algorithms. One uses Turing machines and another uses circuits. So we're going to focus on the circuit language. For this talk, essentially, a quantum algorithm of space S and time t is a quantum circuit with S qubits and T operators. So there are S qubits initialized to the ket 0 state, and there are T operators applied one after the other. So what kind of operators do we allow? This is an important question, and based on the kind of operators we allow, we could potentially get different models of computation. So here are the different types of operators that we allow. In the unitary model of computation, we fix some set of unitary gates that's universal for quantum computation. So for example, we fix the Hadamard and the Toffoli gate, and look at circuits whose operators all are either Hadamard or this Toffoli gate. So this model kind of captures all possible unitary operations that you could hope to implement. So we call this the unitary model. Now, if we allow the algorithm to perform measurements during computation, we get what we call the unital model. So these are quantum circuits where each operator is either a Hadamard Toffoli or a measurement gate. So what's important in this model is that you can perform these measurements during computation. So this is the unital model of computation. Finally, we have a more general model of quantum computation, where we also allow the algorithm to implement this operator called reset operator. So what does this operator do? It maps a qubit in an arbitrary state to the 0 state. So this is a slightly unusual operation. It's not a reversible operation. It's not something that you usually allow in quantum computation. But we can consider a model of quantum computation that allows this operation. One way to think of this operation is to imagine that the quantum circuit has the ability to discard a qubit and get a fresh qubit in the 0 state. Another way to think of this model, it turns out, is that you can think of algorithms with both quantum and classical memory. So these are algorithms on which you have quantum memory on which you perform quantum operations. So by that, I mean reversible operations or measurements. And there's also classical memory on which you can perform classical operations. So for example, you can erase bits. And there is some limited interaction between the quantum and classical part. So for instance, you can copy measurement outcomes from the quantum part to the classical part. And it turns out that this model kind of captures the general model of quantum computation where you can reset qubits. So this turns out to be a very powerful model in the sense that you can simulate measurements using just the reset operator and Toffoli gates. So in the general model of quantum computation, you don't even need measurement gates. You can simulate them using this reset operator and this Toffoli gate. For the rest of this talk, we're going to be ignoring this general model because our focus is in understanding the power of intermediate measurements. So we're going to focus only on the unitary and unital model. So for our talk, the only operators allowed are Hadamard, T.poly, and measurement gates. So there is one technicality here that I have not mentioned. So typically algorithms have an input and an output. And the question is, how does the input and output enter this quantum circuit? So the input is what decides the circuit. So we require that there is a classical log space algorithm, which on input X outputs the sequence of operators and on which qubits they act. So the input defines an encoding for the quantum circuit. And furthermore, we require that this encoding is efficiently computable. Now, how does the output enter the picture? Well, we take the quantum circuit and measure the first qubit at the very end and declare the measurement outcome as the output of the quantum circuit. So this is a probabilistic bit, and we declare that as the probabilistic output of the algorithm. For the rest of this talk, you can ignore this technicality and just work with a quantum circuit with S qubits and T operators. For now, we can forget that these operators actually are defined by some log space algorithm. So any questions about these models of computation?
Should this classical circuit depend just on n, not on the whole string x?
Sorry, could you say that again?
Should this classical log space algorithm just depend on the length n of the input rather than on the whole input?
No, we require it to depend on the input. Right, because there is no other way the input x enters the picture. So the x is what, yeah, the operators depend on x, not just on the length.
Okay.
Concerning your time measure, given the possibility of running some of these unitary operators in parallel, it seems that you are measuring the size of the circuit rather than the depth. Am I correct?
Yeah, I'm not sure how the depth enters, but yeah, you're right. We're not allowing these things to happen in parallel, but typically in our settings, the time is much larger than the space. So we don't really count for the advantage in implementing things in parallel.
Okay, thanks.
Yeah.
Yes, can I just to talk about the thing that you told me to ignore? Why is log space uniform a natural requirement here? Like, why is the algorithm restricted, the classical algorithm restricted to be log space?
So you could do this for classical algorithms, and it turns out that's what you get. So you can define classical algorithms of time, t, and spaces using Turing machines or using this language. And this is what you'd get. Yeah. Yeah, so there is a question about, yeah.
From the classical world, this is a natural constraint. Okay.
Exactly. Yeah.
And so you assume that the circuit runs on all zero, the qubits are all initialized to all zero?
Yes. So yeah, there is an example in the next slide. So this is the picture to keep in mind. So always the initial state is all zeros. There are T operators, and yeah. Okay, so any other questions about what our model of quantum computation is? Okay, great. So now I'm ready to state our main problem of interest, and this is the problem. Given a quantum algorithm with intermediate measurements, can we simulate it by a quantum algorithm without intermediate measurements? So are unitary quantum algorithms less powerful than algorithms that can also perform intermediate measurements? Do intermediate measurements give power to quantum computation? So this is a really fundamental question in quantum computing. This asks about what is the power that measurements give quantum computers. Another reason this question is interesting is from the perspective of reversibility of computation. So measurements are not reversible operations. So one can ask, can we simulate measurements using reversible operations? So one reason to make things reversible is that certain techniques are known for reversible algorithms. So for example, space and time efficient error reduction is known for reversible algorithms. So reversibility is a desirable property to have. And this question asks, can we simulate measurements by reversible operations? So this is the question we're trying to study. What do we know about this question? So one of the first things we study in quantum computing is the principle of deferred measurements. So this gives us a way to eliminate intermediate measurements. So this is saying that these two operations are equivalent. So on the one hand, you have a measurement of a qubit. On the other hand, you have this operation where you copy this qubit onto a fresh qubit using a controlled NOT gate, and then you ignore this qubit for the rest of the computation. The principle of deferred measurement says that these two operations are equivalent. So in other words, instead of measuring a qubit, you can copy this qubit onto a fresh ancillary qubit and ignore that ancillary qubit for the rest of the computation. This principle implies that quantum algorithms of time t and space s with intermediate measurements can be simulated by algorithms without intermediate measurements in time t and space s plus t. So why s plus t? Because this algorithm could potentially perform t measurements, and to defer each of these measurements, you need a fresh qubit. Now, this is very efficient in time, but it's not efficient in space. So think of the setting when S is polylog t. In this case, your space goes from polylog t to t. So it's an exponential blow up in the space. So the principle of deferred measurements is not space efficient as it is stated here. So one can ask, is there a principle of deferred measurements that is space efficient? Can we eliminate intermediate measurements using very little space? So this was an open question until very recently it was solved. It was shown that indeed there is a space efficient elimination of intermediate measurements. So it was shown independently by these two works that quantum algorithms of time t and space s with intermediate measurements can be simulated without intermediate measurements in time poly t 2 to the s and space s plus log t. So typically s is at least log t. So this overhead in space is a constant multiplicative factor. However, the blow up in time is really large. So again, think of the setting when s is polylog t, but s is much larger than log t. In this case, your time goes from polynomial to 2 to the polylog t. So this is a quasi-polynomial blow up in time. So with regards to the open question that I just stated a few slides ago, the best known simulations of algorithms with measurements by algorithms without measurements required either time 2 to the s or space t. So we had space efficient simulations, we had time efficient simulations, but we did not have a simulation that was both time efficient and space efficient. So this is where our work enters the picture. So our main theorem is that we can defer measurements using very little time and space. So quantum algorithms of time t and space s with measurements can be simulated with 1/4 error by quantum algorithms without intermediate measurements in time T.poly s and space S.log T. So in other words, we give a version of the principle of deferred measurements that is both space efficient and time efficient. For example, if you look at algorithms whose space is polylogarithmic in the time, so think of algorithms whose space is polylog n and time is polynomial in n, we show that such algorithms don't require intermediate measurements. So this is our main theorem. Any questions about our main theorem?
I have a question. Sorry.
Yeah.
So I'm wondering, so you do this, what would this intermediate measurement do exactly? So it would measure a qubit and then it gets an answer, or it measures maybe several qubits, and then are you allowed to do some kind of computation on those and then feed back into your circuits, like in fault tolerant computation?
Yeah, so this is a slightly tricky point. So how can measurement outcomes really change what happens in the circuit? So we don't have the ability to remember the measurement outcome. But what we can do is look at the state after the measurement, and controlled on that state, we can perform some unitary or something like that. So, so in this picture, the outcome of this measurement is something that we can't really write down, so to speak. But what we can do is take a fresh qubit and do a controlled XOR or something. So in some sense, you can remember the measurement outcome and do some computation based on that, but you'll have to pay for the space required to store the outcome. So in some sense, the power mainly comes from the fact that it collapses states, so to speak.
Okay, good. Because yeah, that will be a next step, right? I mean, you do some meaningful classical computation on it and then feed that back into your circuit.
Right. Yeah, the thing is, once you allow classical computation, you need to be able to allow the ability to erase memory outcomes or erase the measurement outcome. And once you can do that, you can kind of get rid of the measurement. So this question is really interesting when you only have quantum memory.
Okay, thanks.
Yeah.
I have one small other question. What's the notion of error that you use in your theorem?
The final states are close in trace norm.
Okay, thank you.
Yeah. Okay. So if there are no other questions about our first result, I'll go on to describe our second result. So, so let me first describe the connection between our first result and second result, and then I'll motivate our second result. So the main observation to go from our first result to the second result is the fact that intermediate measurements and randomness are equivalent. So let's see how. So first, intermediate measurements can be used to generate randomness. So for example, take this circuit. Initially, you have the ket 0 state. You apply a Hadamard and then you measure it. So the measurement outcome is going to be 0 with probability half and 1 with probability half. So you can generate a uniformly random bit. And to generate more random bits, you just take the same circuit and apply Hadamard and measurement over and over again. And the sequence of measurement outcomes would be a uniformly random string. So intermediate measurements can be used to generate perfect randomness. Interestingly, the other direction also holds. So randomness can be used to simulate intermediate measurements. So in particular, the measurement of a qubit can be simulated by this operator. So what is this? This is a controlled unitary operator. This unitary operator is just the reflection about the state 1. And this control is on a uniformly random bit. So by uniformly random bit, we just mean a state that is with probability half, it is in this state, and with probability half, it is in this state. So this is a qubit that is in this state. And the claim is that this measurement operator is equivalent to this operator. The proof of this is quite simple. So it is basically these 3 lines that I've written in the slide. I'm not going to go through the proof. But the takeaway here is that as operators, the measurement operator is equivalent to this controlled unitary operator, provided this control is on a uniformly random bit. So therefore, randomness can be used to simulate intermediate measurements. So therefore, the problem of eliminating intermediate measurements is equivalent to the problem of eliminating randomness. In other words, the problem of derandomization. So in particular, if you take quantum algorithm of space S and time t with intermediate measurements, you can produce a quantum circuit without intermediate measurements, but which has access to randomness, at most t bits of randomness. So this is the connection between intermediate measurements and derandomization. The idea here is that instead of using t uniformly random bits, we can use T pseudorandom bits. That is, T bits which contain very few bits of true randomness, and the rest of the bits are a function of these few random bits. So this motivates the concept of a pseudorandom generator, which I will define now. So a pseudorandom generator is a function that stretches few random bits to many random bits. So it's a function from 0, 1 to the little t to 0, 1 to the capital T. Think of little t as much smaller than capital T. The behavior we want of this function is the following. So imagine you have an algorithm f and you're feeding it a uniformly random string over capital T bits and you get some output. We want to mimic this output by using very few random bits. And the way we do that is to take a uniformly random seed over a smaller universe, so little t bits, stretch it using the pseudorandom generator, and then feed it to the algorithm f. We want the output of the algorithm f in this case to be close to the output in the ideal case. So this is the behavior we want out of a pseudorandom generator. More formally, we want the property that for all algorithms of time t and space s which read t random bits, the final state of the algorithm when the random bits are drawn from the output of G on a uniformly random seed, this final state is close to the final state when the random bits are drawn uniformly and independently. So as an equation, we want this property to hold. The expected final state, so by f of r, we mean the final state of the algorithm f on random string r. We want f of g of x, the final state, when x is drawn from 0, 1 to the t uniformly at random, little t. We want this state to be close to the state f of y, where y is truly uniformly at random from 0, 1 to the capital T. So this error, you can fix any norm. So for instance, we work with the trace norm. So this is what a pseudorandom generator is. And the name of the game is to try to minimize the seed length of the generator. So using as few random bits as possible, you want to mimic the behavior of the algorithm on a large number of random bits. So this is a pseudorandom generator. And our second main result is that we show a pseudorandom generator for quantum algorithms of of time t and space s, which read t random bits. So we show that the INW generator is actually a pseudorandom generator for quantum algorithms. So the INW generator, the Impaglia-Sonnesan-Wigderson generator, is a well-studied generator for classical randomized algorithms. So for time t space s algorithms, it uses seed length S.log T. It's also efficiently computable. And it was shown that this generator fools classical algorithms of space s time t. We show that it actually fools quantum algorithms as well for a variant of this generator. So this is our second result. I'd like to remark here that our result holds for even more general quantum algorithms. So you could fix any set of operators, including the reset operator. So our result on PRGs would still hold for those kind of algorithms as long as they read T random bits. But the reason I'm stating it only for algorithms with unitary operators and measurements is that the main motivation for this result is in the application to eliminating intermediate measurements. So for algorithms with reset operations, they can trivially simulate measurements. The second remark I want to make is that to the best of our knowledge, people have not studied PRGs for quantum algorithms which read random bits. And the reason is that presumably quantum algorithms can be used to generate perfectly random bits. But this is assuming that they have the ability to perform intermediate measurements. So with regards to the problem of eliminating intermediate measurements, these objects are naturally come up. So with regards to PRGs for quantum algorithms that read random bits, of course, one motivation is that they can be used to eliminate intermediate measurements. But we think it's also interesting from a more general perspective. So for example, from a complexity theoretic perspective, PRGs give you a distinguishability task. That is the problem of distinguishing a random string from a pseudorandom string. And PRGs show that this is an example of a task that small space quantum algorithms cannot solve. So this is interesting from a complexity theoretic perspective. We also think it might be interesting in the setting when the quantum device cannot be relied upon. So you could have a certain protocol where a quantum algorithm is supposed to use public randomness, or it is required to toss its own random coins and output something. But in situations where the quantum algorithm cannot be relied to generate true randomness, nor can the verifier generate true randomness, we think that PRGs might be useful in ensuring that the protocol behaves as it should. So this is another setting where we think PRGs might be interesting. And finally, from a purely physics perspective, it's interesting to understand how much randomness do you really need to simulate a quantum circuit? How much of this irreversibility is necessary for a certain quantum computation? So we think PRGs might be interesting in all these settings. But of course, our main application of PRGs for quantum computation is in their application to eliminating intermediate measurements. So this completes a description of the second result. Any questions? Okay, so in the rest of this talk, I'm going to focus on proofs. So first I'll begin by making this connection between eliminating measurements and PRGs more formal. So I'll start by describing how to use PRGs to eliminate intermediate measurements. I've already described this somewhat intuitively before, and now I'll go into the exact way we do this.
Maybe Uma, I have one question.
Yeah.
So this pseudo-random generator is just a classical object. I mean, it's a classical computation.
Yes.
So it's not optimized for quantum yet. It could be even more efficient.
That's true. So that's true.
Cool.
Yeah. Yeah, I think the seed length is so the seed length is S.log T, and it's possible that you have to store the seed. So I am not sure if you can get much advantages in terms of the seed, but maybe the runtime can be improved. Yeah, the space might not be improved so much. Okay, so let's see the proof of this. So how do we eliminate intermediate measurements using PRGs? So given an algorithm with T measurements, first we're going to write down an equivalent program, equivalent algorithm which has T random bits and has no measurements. Then we're going to use our pseudorandom generator to replace these T truly random bits by T pseudorandom bits. And the number of truly random bits is only S.log T. So this is what we get from our second result. Now we're going to replace these S.log T truly random bits by S measurements. This is again the equivalence between random bits and measurements. And finally, we're going to defer these measurements. And to defer S.log T measurements, you only need S.log T additional space. So this is how we use PRGs to defer intermediate measurements. So any questions before I move on to the description of the PRG itself?
So you really use you need some seeds, which you really do by an expensive deferring of the measurement, and then you use the seeds to build the pseudorandom bits to get rid of the other random bits or the other measurements.
Mm-hmm. Yeah, the seed is the most expensive part right here, like the fact that you use S.log T truly random bits.
Couldn't you recurse on that somehow?
So my first thought is that you will need to do something better for classical algorithms. And that itself is a really hard question.
Okay.
Yeah, getting better than S.log T even for just classical randomized algorithms sounds like a hard problem. Okay, so now I'm going to move on to the proof of the INW generator. So just to recap what we're trying to show, we have a quantum algorithm of time t and space s, and we have this INW generator, which I'm not going to describe right now. And the property we want is that if you look at the final state of the algorithm, when you feed it truly random bits, you subscript capital T, we want the final state to be close to the case when you're giving it a random string G applied to R. So G is the INW generator and R is a random seed over a much smaller universe. So this is what I'm going to show. So I'm not going to define the generator now, but I'm going to give you the intuition behind the construction of this generator. So let's see the intuition behind the construction. So let's just look at the classical case for now. So you have an algorithm B. You can think of it as a function that takes in a uniformly random string over t bits. So let's call it y1, y2 up till yt. It takes in t random bits. It also takes in an initial state and outputs a final state. Now, take the midpoint of this algorithm and divide this algorithm into two equal parts. So you have B0, which is the first half of the algorithm, and B1, which is the second half of the algorithm. So B0 takes a uniformly random string of t over 2 length. B1 takes a uniformly random string y prime, again of t over 2 length, but that's completely independent of y. And the connection between B0 and B1 is that the final state of B0 is the initial state of B1. Now, the main observation here is that the only information passed from B0 to B1 is the state at time t over 2. So think of how much information B0 leaks about the string y to B1. Any information that it leaks is through the state at time t over 2. And this state is on at most s bits, because this is an algorithm with at most s bits of memory. Therefore, the algorithm B0 leaks at most s bits of information about y to B1. So instead of using y and y prime that were completely independent, one could hope to use y and y prime that are correlated, but not too correlated. The way to formalize this is by means of an extractor. So I'll define extractor in the next slide. But for now, extractor is a function that acts on y and a few additional random bits. So these additional random bits are roughly s. There are s bits of randomness. And the idea is that instead of using y prime, you can use y equals extractor applied to, you can use y prime that is an extractor applied to y and t. Assuming that you can do this, we're in good shape, because effectively we reduce the randomness from t to t over 2 plus roughly s. So this t over 2 comes from the randomness for y, and this s comes from the randomness for d. So what this extractor does is, instead of having two completely uncorrelated inputs, you have two correlated inputs that are correlated by this extractor. And this extractor has to inject very few bits of randomness and still preserve the property that these algorithms behave as they should behave. So this is the idea. And in the construction of the generator, we will recurse on this idea on both sides, and essentially until all the programs are of constant length. So we're doing this recursion log t times, and each time you're reducing the randomness from t to t over 2 plus s roughly. So doing this log t times, you get a seed length of S log T.
Does this require that the random bits are classical in the sense that you can reuse them?
I'm not sure what you mean by reuse them, but yeah, in the sense, yeah, we do use the
random. You have
random.
this string y, and basically you are reusing it in the second part. But if the first part of the algorithm has consumed it, for example, if it would be quantum information, you can only use it once.
Yeah, we do reuse it. So in some sense, we imagine that this randomness is written down on some tape that we can go back and look into. So yeah,
then
it's quite classical
information.
Yes.
Thanks.
Yeah.
Can I also ask a question, Uma?
Yeah, sure.
So this extractor is not perfect in the sense that the random variable that it outputs, it will have some positive total variation distance compared to truly uniform distribution. Is this not going to add up over the log T times that you do this?
Exactly. So this is going to add up. So for the smaller steps, we're going to require the error to be like epsilon divided by 2 to the I. So if you want a final error of I, epsilon, we're going to have, in the subsequent steps, we're going to have higher accuracy. So we're going to require epsilon over 2 to the I or something like that. So yeah, there is a careful error analysis that needs to be done.
I see. So you don't get log T factors in addition to what you have?
We don't, yeah.
I see. Thanks.
Yeah. So any other questions about the motivation for the generator? So I'll start by, I'll define extractors formally now, but yeah, any other questions at this point? Okay, so let's see what extractors are more formally. Okay, just to recap, this is the thing that we're trying to prove now. We want to show that if you have an algorithm, instead of using two random inputs y and y prime that are independent, we want to say that we can use y and y prime which are correlated. So we can use extractor applied to y comma s instead of y prime. So this is what we're trying to show. Now let me look at, now I have to define extractors. So what is an extractor? I'm not going to define it formally, but for this talk, this is what you'll need. So imagine you have Alice and Bob. Alice has a uniformly random state ket y. So y is a random string over some number of bits, and she has a uniformly random y. Bob looks at y and writes down some information about y. So let's call this row y. This is some quantum state on at most t qubits. So Alice's and Bob's state are correlated. Now apply an extractor to Alice's input and some additional uniformly random seed S. So this is a function that takes in these two inputs and outputs something. The property we want of an extractor is that applying the quantum extractor kind of decouples Alice's and Bob's state. So what we want is the final joint state of Alice and Bob after the application of an extractor should look like a tensor product state between Alice and Bob. It should look like Alice had a uniformly random y prime and Bob had a uniformly random row y, that was where y is independent of y prime. So an extractor using very few bits of randomness is able to decouple Alice's and Bob's states. So here is a formal definition. We say that a function x is a weak quantum extractor against t qubits if for any collection of states that Bob could store on at most t qubits, you have that the final joint state of Alice and Bob, after you apply the extractor to Alice's input, is close to the final state when Alice and Bob had like completely independent inputs. So this is what an extractor does for our purposes. And the thing we're trying to optimize here is the seed length of the extractor. By injecting very few random bits into Alice's input, we want to decouple Alice's and Bob's inputs. So that's what an extractor does. So such objects have been studied a lot. And in particular, we're going to make use of this extractor due to Fair and Schaffner. They show a weak quantum extractor against t qubits with seed length roughly t. So this is saying that if Bob stores a state on at most t qubits, you only need to inject roughly t bits of randomness into Alice's input so as to decouple her input from Bob's input. So let's see how to use extractors in our setting. So I claim that the setting we have for space-bounded algorithms is exactly the same as this setting. So how is it? So let's look at B0 and B1, which are the first and second half of the algorithm B. Imagine giving Alice a uniformly random string y and give Bob B0 of y. So give Bob the final state of the algorithm B0 when you give Alice's input as the random string. Now this is a state on at most s qubits. And now we're in the exact same situation as before, where the side information that Bob has stored about Alice's input is basically the final state of the algorithm B0 on Alice's input as the random string. So now when you apply an extractor to Alice's input, using roughly S bits of randomness as the seed, you get this as the final state. And by property of extractor, we have that these two states are close to each other. So on one hand, you have extractor applied to Y and S and B0 of Y. And on the other hand, you have completely random Y prime that is independent of Y and B0 of Y. So by the extractor property, these two states are close on average over Y and S and Y prime. So now we're almost ready to complete the proof. Imagine running the second half of the program using this as the randomness and this as the initial state. In the first case, you get B1 applied to extractor YS as the randomness on the initial state B0 of Y. So if you think about this, this is exactly what the algorithm B does when you give it the random string Y followed by extractor of YS. In the second case, you have B1 acting on the random string Y prime applied to the initial state B0 of Y. Now this is the same as the algorithm B acting on the random string Y followed by Y prime. Because these two states are close, you have that these two states are close. So in other words, if you take this algorithm B and apply two correlated inputs Y and Y prime that are correlated by an extractor, the final state is close to the final state when you have two truly random Y and Y prime. So this is the intuition behind why we can use extractors to reduce the amount of randomness. So any questions about this overview? Okay, so I will go on to describe the generator in a little more detail. So I'm just doing it because this is something not all of you might have seen. Before that, I wanted to make a comment on the actual extractor that we use. So we rely on this particular version of the extractor because it has some nice properties. So let's look at them. So the extractor that we use is based on delta bias spaces. So very informally speaking, a delta bias space is a collection of vectors such that if you look at the parity of any subset of coordinates, the parity is going to be unbiased, roughly unbiased. So this is the way to formalize this. Another way you can think of it as a distribution over points in 0, 1 to the n for some n, such that the moments of this distribution are all small. Or in other words, the Fourier coefficients of these distribution are all small. So you can think of it as a collection of points that is very far from a hyperplane over F2, so to speak. So these are objects that have been well studied. And the extractor that we use is defined by Fur and Schaffner. So this extractor is defined as given Y and a seed S, the output is Y plus A subscript S. So A subscript S is the sth element of the delta bias space. So these are the extractors that we use. And one useful property of these extractors is that they're reversible in the sense, given Y and S, you can compute Y plus AS. And given Y plus AS and S, you can recover Y. So this is useful because given the seed length, we want to compute this generator and we want to do it reversibly. So with regards to reversible computation, this is a very useful property to have, and we actually use this. So these are the extractors that we use. In the next 5 minutes or so, let me just describe the INW generator and sort of hand wave over why it works. So here is the actual generator. So you fix parameters m, which is roughly log t, and n, which is roughly theta s. and assume that we have extractors that work against inputs and outputs of length in and that work against S qubits of information that Bob could store. So this generator is going to be defined recursively. The ith generator is going to stretch I+1 times n random bits to 2 to the I pseudorandom bits. Finally, we want capital T random bits. So we're going to look at G subscript log T or G subscript M. So this is called, GM is called the INW generator, and the definition is as follows. So G0 of X is simply the first coordinate of X. If you have GI applied to W, SI, so W is the first IN parts of the seed and SI is the last N bits. So we define GI of W, SI to be GI minus 1 of W. So this is defined by recursion, and GI minus 1 applied to extractor applied to W, SI. So on the one hand, on the left hand side, you have GI of W. On the right hand side, you have GI applied to an extractor applied to W. So this is the INW generator. And to show that it works, we use induction, and we show that GI is a pseudorandom generator for algorithms of time 2 to the I, where the error is extremely small. So the error is 3 to the I over T square. So the smaller I has smaller error. And finally, when we set I to be log T, we get that GM is a PRG for quantum algorithms of space S and time T with small error. So here we actually get inverse polynomial in T, but finally what we want is just constant error. So this is the claim. And this is really getting into the details, but let me quickly show you how this claim is proved by induction. So we want to show that if you have B acting on Y and Y prime that are completely independent, this is close to B acting on G of I, W, SI. So we're going to show that the ith generator works. And the way we do this is in 3 steps. So in this first equation here, I'm replacing Y by GI minus 1 of W. In the second step, I'm replacing Y prime by GI minus 1 of W prime. Finally, I'm replacing W and W prime by W and extractor applied to W and SI. The claim is that these 3 steps suffice because the generator was defined recursively so as to satisfy the property that this thing here is exactly the output of the ith generator. So this thing here is exactly GI of W, SI. So let's quickly see the justification for these 3 steps. So the first 2 steps are going to follow by induction. So here you're taking a program of length 2 to the I minus 1 and replacing the random string by the output of the I minus 1th generator. So this step is justified by induction. The second step is also justified by induction. For the third step, you have a very similar setting as before. You have W and W prime that are completely uncorrelated on one hand. On the other hand, you have W and W prime that are correlated using an extractor. So here you have W, W prime, here you have W and extractor applied to W and a uniformly random seed. Using the extractor property, we're able to show that these 2 states are close to each other. So this justifies step 3. So these are a lot of details, but the main idea is how we use induction and this extractor property to build this generator and how it's proved. So any questions about this? Okay, so let me summarize my talk now. So to summarize, our first result is that quantum algorithms of small space and time with unitary operators and intermediate measurements can be simulated by algorithms with only operators and without intermediate measurements in very little time and space. So if your original algorithm was of time t and space s, then our simulation runs in time T.poly s and space S.log T. So in other words, we give a version of the principle of deferred measurements that is both space efficient and time efficient. Our second result is that we study pseudorandom generators for space-bounded quantum computation. We show that a variant of the Impaglia-Sonissan-Wigderson generator actually fools small space quantum algorithms. So this brings me to the end of the talk. Any questions?